Hello, 8th graders. Today we're going to wrap up our conversation around gravity. And today is actually one of my more favorite topics because it's one of those in physics where a lot of people think that they understand or that there's some logical answer to this particular question. And most people actually turn out to be pretty wrong. So if you happen to be one of those people who have that misconception about gravity that we're going to talk about, I hope by the end of this video, you're able to say, I used to think this, and now I totally understand it. And you're going to be in that small minority of people who actually understand something that is so constant in our universe, like gravity, that most people don't actually understand. For today's lesson, you need to make sure that you have completed the warm-up first. It's a Google form that's in Google Classroom. If you haven't done that, pause this video, go take care of that first. And of course, you're going to need your notebook with the note side and a practice side. Please make sure that you have added a nice big header at the top of a fresh, clean page. It should say Part 5, What Causes and Affects Gravity, so that you can keep your notes organized and you can find this section again when it comes time for the assessment. The objectives for today look like this. There are actually 3, and they kind of merge into each other, so we're going to kind of cover them a little bit overlapping. So the first one is to be able to describe how Newton's third law is at work in an example. So I know that Newton's third law is the next unit, but we have to have a little introduction to it to understand this topic that we're going to talk about today. Objective number 2 is to describe the factors that affect gravity. There are actually 2 factors, and you're going to be able to describe both of them pretty well. And then the last one merges into the second one. You also need to describe how those 2 factors affect gravity differently. So each of them affect gravity, but they do it in a different amount. And you're going to be able to describe those things. So we have to first start with Newton's third law. So over on your note side, I need you to please add the law that's on their screen. You've probably heard this one before. This is usually the one that people have memorized out of all 3. So you've probably heard it as for every action, there is an equal and opposite reaction. And that's definitely true, but I don't think that it's a little misleading. A better way to say it would be for every force, there is an equal and opposite force. Since we've been talking a lot about force, hopefully you're feeling pretty comfortable with what a force is. It's a push or a pull. And basically Newton said that they always come in pairs, these forces. They have to. It's one of his laws. And so here's an example. So this guy that's sitting on a little car, he throws this heavy ball to the right. And that's the action. So you've heard of probably for every action, there's an equal and opposite reaction. And so if he pushes the ball, it goes flying to the right. So he had to put a force on it. Well, Newton said that there has to be a force in the other direction and of the same amount in order for that to be true. And you can see that because the cart goes rolling back a little bit. So for every force, there's an equal and opposite force. So as he pushes to the right, the cart gets pushed to the left. So a lot of times people get hung up on this because they're like, well, wait a second, how come the ball is going so fast to the right and he's going so slow? Well, think about it like this. Suppose the force that he's putting on that ball is 10 newtons. So he's pushing on the ball with 10 newtons. That means that he's getting a push in the opposite direction also of 10 newtons because equal and opposite has to be equal. And so if you think about what we've just done with Newton's second law, since the ball is so small, if you apply 10 newtons to a small thing, it's going to go fast. And since he and the cart are so much bigger, if you apply 10 newtons to a bigger thing, it goes slow. But the forces are equal, and that's what Newton's third law is all about. So the man's mass is bigger, and so the bigger mass requires more force to accelerate. And that's why you'll see the cart just go a little bit, but the ball go fast. Let's take another example. Over on your practice side, I need you to make a little sketch of this man, and I want you to draw in some of the force diagrams. Pause this video if you can make a guess. Here's what he's doing. All he wants to do is walk to the left. So what forces are at play in order to make somebody just walk? Pause the video and make a guess. So there have to be 2 forces because Newton's third law says that equal and opposite, there always have to be 2. So if you're going to be walking, that's the action force, and that should just be the arrow pushing to the right. So if you want to walk to the left, that means that you have to push on the ground in the opposite direction. Think about that. If you want to start running that way, you have to push on the floor that way in order to start doing it. So the action force is to the right. The reaction force, what happens because you push on the floor, makes you move to the left. So you're actually So you're actually pushing on the earth in order to make the earth push back on you. And both things get the same amount of force. Here's a pulling example. Sometimes this one is a little bit of a brain bender for some people, but both of those pushes and pulls operate the same way. So make another sketch on your practice side of somebody pulling on a rope and add in the action force and the reaction force and label them. Pause the video and label those, come back and see if you're right. So the action force, like where the force is starting, is with the person pushing on the ground. So he pushes on the ground to the right with his feet. The reaction is that the rope gets pulled to the left, and there's your reaction. And the thing is that both of those forces have to be the same amount. So to kind of wrap up our little first objective about an introduction to Newton's third law, I want you to take one of these examples that's on your screen. These are all examples of Newton's third law. And I want you to, on your practice side, do a quick write. So write down quick write so I can find your writing when I look at your work. Choose one of these scenarios and explain in a sentence or two what the action force is and what the reaction force is. Pause the video and go for it now. So if you are still watching, you have paused and you've done a quick write. Let's look at a couple of them. If you have ever filled up a balloon and let it fly around the room as the air escapes, the balloon is pushing the air out one side, and then the air pushes on the balloon in the exact opposite direction. And this is exactly how a rocket would work too. As the rocket pushes out fuel, the rocket gets a push in the opposite direction. If you've ever fired a rifle, you put a force on the bullet that goes out of the gun, and the bullet puts a force on the gun that punches it back into your shoulder. Both are equal and opposite forces. With a bird, if a bird wants to fly up into the air, he has to push on the air, and the air is going to push right back on him, and it's equal and opposite. This one's a little bit misleadingly simple. We've already talked about normal forces, and we're going to go into it more in just a second. If you have some object that's sitting on a table, it's pushing down with its weight, and the table pushes right back with normal force. So we've actually already kind of done Newton's third law in a way. Normal force is an example. And then this girl who's swimming, if she wants to go that way and start swimming through the pool, she has to push on the wall with her feet in the opposite direction. All of these are equal and opposite forces. Now let's get into the crazy part. So over on your note side, this is the reason why I had to show you Newton's third law in order to talk about gravity. And this is the part where sometimes people's brains go, wait, that can't be right, but it really is. And you have evidence of this in your world, and let me show you. So for every force, there's an equal and opposite force. Let's talk about the forces that are caused by gravity. So you can tell that the sun is pulling on the earth, and so is the moon, because of tides. If you've ever been to the ocean, and if you remember from 7th grade, the sun and the moon are pulling on the earth, and we can see it because the water moves around the earth depending on where the sun and the earth, or the sun and the moon are relative to the earth, and we see tides go up and down. Well, let's consider the force diagram that might be happening here. So I've got the sun and the earth, obviously not to scale, but I want you to think about how there are pushes and pulls on these two things. So the sun pulls on the earth with a certain amount of force because of gravity. So gravity causes forces. We've already talked about that. And so the sun is going to pull on the earth. But here's the thing. Newton's third law says that the earth also then has to pull on the sun with the same amount of force, because of Newton's third law. So every time that you see the tides, you'll know that, oh, the sun is pulling that water, but also the earth is pulling on the sun. So if you really think about it, maybe the sun also has tides. I don't know. Somebody would have to go there to find out. But think about the force diagram. There would be two arrows pulling in equal and opposite directions on these two bodies. So let's stick with this for just a second. We've already talked about normal force and weight, so let's go back to that. We're still talking about the same idea here with gravity. So we already know that gravity causes weight. You're pressing down on your chair or on your floor or wherever you are right now because you have mass, and the acceleration of gravity pulls that mass down. Well, your weight causes normal force to happen. So as you push on the floor pushes right back. And we know that those two arrows have to be equal because, hopefully, you're not accelerating. You're balanced. You're just staying put. Those two arrows have to be the same. Well, let's think about something that's a little bit crazier. Let's go back to the skydiver for just a second. As that skydiver is falling towards the Earth, he still has a weight. He's got mass. The acceleration of gravity is pulling him down. So he's still got a downward force due to his weight. He's got a mass. Gravity is still a thing. So there is a force of being caused by gravity pulling him down. Well, that means that there must also be a force being on the other direction. So his action, his man being pulled down by gravity towards the Earth, but there also has to be an upward arrow too. That means that the man is also pulling on the Earth, and with the same amount of force. Think about that for a second. Every time you jump up into the air while you are airborne, you can tell that gravity is pulling on you because you eventually come back down. But the truth is that you and the Earth are moving apart from each other and then moving back towards each other every time you jump off the surface of the planet. The reason why it feels like only you are moving, though, is because the Earth has way, 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 way more mass than you, and a force put on you makes a bigger difference than the same force put on a huge planet. Push on the Earth, it's hardly going to move at all, but technically it moves, according to Newton. So let's get to the misconception part. I told you that there are some things that some people have a misconception about with gravity. Let's just address it right out, and if it's in your mind, work to remove this from your mind. So here's the misconception. Newton's third law does not say that for every acceleration, there's an equal and opposite acceleration. So when you run and you push on the Earth and you start to accelerate at however fast you can run, that doesn't mean that the Earth is going to accelerate at the same amount too. That's not what Newton said. He also didn't say that for every velocity, there's an equal and opposite velocity. So as you're driving down the road at 60 miles an hour, and your car is pushing on the road to make the car go forward, that doesn't mean that the road is also moving at 60 miles an hour in the opposite direction. It's not about acceleration. It's not about velocity. It's about force. It's a push. So if you applied the same force to a person and to a planet, which one would move more? If you push on yourself with 100 newtons and you push on Earth with 100 newtons, which one's going to move more? Hopefully that feels pretty obvious. We just got done with Newton's second law, and that's what it's all about. So if those two objects, the skydiver and the Earth, are receiving the same force, let's apply it to Newton's second law. Does the Earth technically start to accelerate towards the skydiver? Yes. Since there is this reaction arrow pulling up on the Earth, there's a little bit of force being applied to the Earth, but a little bit of force applied to a great big object means like a ridiculous teeny tiny amount of acceleration. But technically, the Earth is accelerating up to meet the man. It's just the man is accelerating a lot more because he's receiving the same force and he's a smaller mass, and so he's going to accelerate faster. So yes, but it's a crazy small amount, and that's all because of Newton's second law. Force equals mass times acceleration. Here's where we're at with our objectives. So far, we've described how Newton's third law is at work in an example. Equal and opposite forces, and we've even applied it to gravity a little bit, but our next step is to go and describe the factors that affect gravity so that we can get into the real topic of this lesson. So on your note side, there are two factors that affect the amount of gravity that some object would feel. The first one is how far apart objects are. So the closer you are to an object, the more gravity you're going to feel from that object, and how much mass an object has also affects gravity. And that's it. So I want you to think about what that means, is that any two objects in the universe, as long as they have mass, they're pulling on each other. There's gravity. It just takes a really, really big object to feel it. So for example, if you have a pencil sitting on your desk, your pencil has mass, and so do you. And since you both have mass, there is some pull between the two of you, and it's equal and opposite. You're pulling on your pencil with some amount of force, and the pencil is pulling right back with some amount of force. The reason why you don't feel it is because those two objects, you and the pencil, are so ridiculously tiny in comparison to what it takes to actually feel these things that you don't feel a thing. It takes objects as big as the planet in order for us to start feeling those forces, but it doesn't mean that they're not there. They are still present. So if you imagine all the objects around you, There are all these force diagrams, all these arrows that you just can't feel because they're so teeny tiny. But if you take a whole bunch of stuff and you put them together, then you would have enough mass to actually experience the gravity. So on your left-hand side, on the note side, make sure that you have these 2 yellow boxes written down. Now let's take a look at the picture that I have. So if we're going to take Earth as our first piece of mass, let's talk about these 3 objects that are sitting on the Earth and how much force they feel relative to each other. So each object is pulling on each other. So the space person is pulling on the Earth, and the Earth is pulling on the space person. The person standing on the surface of the Earth and the house both have forces between them also. Let's take the house. The house is a relatively big object, and so it has a big weight. It's pressing down on the Earth. Imagine trying to put your hand under a house. That would crush your hand. It's because it has a lot of mass, and the Earth is pulling on it with a lot of force. But the house is also pulling on the Earth with the same amount, so they have the same arrows. If you took the person standing on the surface of the Earth, they're the same distance away from the center of the Earth, but now that the person is much smaller in mass, there are smaller arrows. Well, what if you were to take a small person and move them far away? If you move a person way out into space, now the mass is tiny and the distance is great. That means that there's still a force, but it's a really tiny arrow. So if you were to imagine going way, way, way out into the depths of space, we've talked before about saying how that there's no gravity, but that's not technically true. If you move way far away from the Earth or other stars, there is still technically some teeny tiny small amount of gravity. It's just so tiny that you wouldn't be able to feel it at all. If while you're looking at this picture you're wondering to yourself, well, why doesn't that astronaut start falling into the Earth? As long as there's an arrow there, shouldn't they start accelerating towards the Earth? And if you're thinking about that, I've left a link on the screen that talks about why things don't fall into the Earth, instead they orbit. And I know you've talked about this a little bit in 7th grade, so we're not going to spend any time on this. But if you're curious, I found a pretty good video. You can go and watch the link that's on your screen. In Google Classroom, there is a document that starts with a couple of boxes that look like the ones that are on your screen. Your next step is to go to that document and start filling in the apply questions. Pause the video and go take care of that now. For the first one, if you're in a spaceship getting closer and closer to the sun, what will be happening to the force you feel? Well, since distance is one of the things that affects gravity, as you get closer and closer, you would feel more and more force from the sun. The second question says, if you take off in a rocket and go to Mars, what will happen to the force of gravity you feel from Earth as you get further away? Well, as you start moving away from Earth, the gravity will decrease and decrease. And actually, as you start getting closer to Mars, you'll start to feel the gravity from Mars start to increase as you get closer. So if you imagine the gravity from Earth like this, and the gravity from Mars like that, as you start traveling away from Earth, those 2 bars at some point are going to pass each other, and then you'll feel more gravity from one place as you get closer to it. The last one says, as Mr. Nelson is getting fatter, as he gets older, he gains more mass. What is happening to the amount of force I feel from gravity? Well, the amount of mass is the other thing that affects the amount of force from gravity. So more mass, more force. I'm feeling more press on the Earth as I get older and fatter. For our objectives, we've done the describing parts. We've taken our notes and we've taken care of the first 2 objectives. We've described how Newton's third law is at work in an example, and we've described the factors that affect gravity. This is a good midpoint for you to go and take a short break if you need one before we jump into the third objective, which is talking about how those 2 factors affect gravity differently. Pause the video and go take a break. So we know that mass and we know that distance are the 2 things that affect gravity, but they don't affect gravity in the same amounts. So like if you double the amount of mass that an object has, that's not the same as doubling how far away it is. That's not going to make the same difference. So that's what our mission is now, is to figure out, well, which one affects gravity more? Is it the mass or is it the distance away? So there's this equation called the law of gravity that looks like what's on your screen, and it looks very scary. We're not going to use it very much. There's an online calculator that you're going to use that plugs in all the numbers for you and does the math for you, but I want you to at least see what it looks like. So here's what it's all laid out like. So on the top, you would take this gravitational constant, which is just a set number, and the 2 masses of the object. So the Earth and the person, or the space shuttle and the star, whatever 2 objects you're comparing to each other. and you multiply those together, and you divide it by how far apart they are squared. And that's how you figure out what the force from gravity is. So if you're interested in actually using this equation, you totally could bust out your calculator and punch in the numbers that you know. But again, we're going to use an online calculator to do all the work for us. And the online calculator is linked in Google Classroom. There's also a tiny URL here, and it looks like what you see on your screen. Let me show you what it looks like live. So here's the calculator here. One of the most important steps is to make sure that you have all of the units set correctly. So I've been playing with this for a while, and I can't remember if I already had them set or if this is the default. But make sure that the two masses are in kilograms, and make sure your distance is in meters, and make sure your force is in newtons. It gives you a whole bunch of other choices, so make sure that you've chosen the right ones. Otherwise, your numbers are going to be very different from the ones that I'm going to show when you look to see what your answers are. Back in the document that says that's called Gravity Investigation, here's what your next steps are. In these three boxes is where you're going to start. The first thing that you need to do is figure out some of these forces using the numbers that I've given you right here. So we're talking about objects out in space like the moon and the sun and Earth, and those things have really big distances between them and really big masses. So we're going to be punching in some pretty big numbers. Get ready to punch on the 0 key a whole bunch because, for example, the sun's mass is 2 times 10 to the 30th power kilograms. And I've left you a little cheat here. That's a 2 with 30 zeros after it. And you're going to need to punch those numbers in order to figure out certain amounts of gravity. Once you've figured out these first three boxes, then you're going to make a little graph because we want to figure out how does the force of gravity change as you move away from an object. So I've given you a whole bunch of distances, and you're going to use the calculator to figure out what those forces are. Once you've used the calculator to figure out all of these forces, you're going to put it into a Google Sheet. Just make a brand new blank Google Sheet and make a line graph. And I want you to paste your graph here and then just fill out the rest of the form. You're going to do the same thing that you just did by making a graph with masses, and hopefully what you'll see is you'll be able to compare those two graphs. Which thing affects gravity more? Is it the masses of the objects, or is it the distance between them that affects gravity the most? So now it's time to pause the video and go get to work using the calculator and filling out the form. And these are all of your steps. Pause the video, go work on that now. If you're still watching, you have finished and you have figured out the difference, and you have determined that distance has a much greater impact on gravity than the masses of the objects do. So as you start moving away from some object, the amount of gravity that something feels drops off really, really quickly. Whereas mass is more of a linear thing. As you cut the mass in half, you cut the force from gravity in half. If you double the mass, you double the amount of gravity. So distance has a much bigger effect. So we've answered all three of our objectives, and now it's time to go to the closure. On your practice side, I need you to clearly write out closure so that when you take a picture of it and attach it, I can find it. These are the two questions that I need you to answer. Number 1, somewhere between the Earth and the Moon, the gravitational force on a space shuttle would cancel. So you would have the same amount of force between those two objects at some point. Is that location closer to the Moon, or is it closer to the Earth? Explain your answer. Number 2, which is greater, the gravitational pull of the Moon on the Earth, or that of the Sun on the Earth? And you've solved this. You actually should have those numbers on your sheet that you've just filled in. And so which one has a greater effect on our ocean's tides, the Sun or the Moon? Hopefully you remember from 7th grade that there are lunar tides and that there are tides caused by the Sun. Which one is greater, and explain why?